Bismillah Rahman Rahim. Find I in the circuit of figure 1. So this is figure 1 here. So and we are supposed to find this current I through this circuit. So as you can see, we have a delta combination of the circuit elements, and we have a delta combination here, and we have a delta combination here. For example, this branch is neither in series nor in parallel with either with this branch or this branch. Similarly, this branch is neither in series nor in parallel with either this or this or this branch. So any of the branches are not in series or in parallel with any other branch. So we cannot use conventional circuit reduction techniques using serial and parallel combinations. So we need to first transform one of these delta combinations in the equivalent Y combination. So let's begin the solution. And it will be convenient if we redraw this diagram and also draw the equivalent Y combination. So for example, this is the uh, delta combination, one branch of the delta combination we have. This is the other branch, and 8 ohm, and this is 8 ohm, this is J5 ohm, this is minus J3 ohm, this is J4 ohm, and then we have uh, a resistance here which is 10 ohms, then 5 ohm in uh, series with minus J2 ohm, 5 ohm and minus J2 ohm, and this is connected with this source here, 30 angle 0 degrees volts. And for example, we can transform any of these delta combination, any two of these delta combinations into the equivalent Y combinations. Uh, let's transform this delta combination, low delta combination, into the equivalent Y combination. So the equivalent Y combination, let's draw the equivalent Y combination here, right? So let's this designate as A, this B, and this as C. So we can then label this combination as this branch as ZC, this branch as ZB, and this branch opposite to A as ZA. Similarly, we can label this impedance here Z1, this as Z2, and this as Z3. This is Z3 here. So the transformation from delta to Y, delta Y transformation is our first step. So we need to express Z1 in terms of ZA, ZB, and ZC. So Z1 is equal to the product of the adjacent impedances divided by the sum of all the impedances in this delta combination. So the product of the adjacent impedances, this is ZB and this is ZC. So this is ZB multiplied by ZC divided by ZA plus ZB plus ZC. So Z1 is equal to ZB is 5 minus J2, 5 minus J2, and that is multiplied by ZC, which is 8 plus J5, 8 plus J5, and we sum all the branches, all the three branches of the delta combination together. So that is uh, 5 minus J2, 8 plus J5, and and plus 10 here. So Z1 is equal to 5 into 8 is 40. 5 into J5, that is plus J25, and then minus J 2 into 8 is 16, and minus J2 multiplied by J5. So minus J into J is minus J square. So J square is equal to minus 1. So minus 1 into minus 1 is plus. So that is plus 10 here. And that is divided by uh, 10 plus 8, 18 plus 5, 23. Minus J2 and plus J5 is plus J3. So Z1 is equal to 40 plus 10 is 50, and plus J9. 25 minus 16 is 9, right? Divided by 23 plus J3. So Z1 is equal to, let's transform this into the rectangular form first before the division. So into the polar form before the division. So this is 50 and plus J9. So that becomes 50.8 angle 10.2 divided by, this is 23 and plus J3. So the polar form is 23.19 and the angle is 7.43 degrees. So Z1 is equal to 50.8 divided by 23.19, and that is equivalent to 2.19, and the angle is 10.2 minus 7.43, that is equal to 2.77 degrees ohm. So let's express this in rectangular form also. 2.19 and 2.77. So that is 2.187 plus J 0.106 ohms. So that is Z1. We have found Z1 here in terms of ZA, ZB, and ZC, using ZA, ZB, and ZC. Similarly, we can find Z2. This is Z2 here. So Z2 is equal to the product of the adjacent impedances divided by sum of all the impedances in the delta combination. So the adjacent impedances are 10 multiplied by 8 plus J5 divided by the sum of all the three impedances in the delta combination, and we have found the sum, already found this sum here in this denominator to be 23.19 and angle of 7.43 degrees, right? So that is Z2 is equal to, we need to transform 8 plus J5 into the polar form. So that is 8 plus J5, and that is 9.434. 10 into 9.434 434, and the angle is 32 degrees divided by 23.19 angle 7.43 degrees. So Z2 is equal to 10 into 9.434 divided by 23.19, and that is equal to 4.068, and the angle is 32 minus 7.43, and that is 24.57 ohms. And we can express this in rectangular form also. 4.068 and 24.57. This is 3.7, and plus j 1.69, 1.69 ohms. This is Z2. Uh, Likewise, we can determine Z3. This is Z3 here, and this is equal to the product of the adjacent impedances. Again, this is 10 into 5 minus J2 divided by the sum of all the three impedances in the delta combination, and we have found the sum already here, 23.19 angle of 7.43 degrees. So we first transform 5 minus J2 into the polar form. So this is 5 minus J2, and that is 5.385. So that is 10 into 5.385, and the angle is minus 21.8, minus 21.8 degrees divided by 23.19 angle of 7.43 degrees. So Z3 is equal to 10 multiplied by 5.385 divided by 23.19, and that is given by 2.322, and the angle is minus 21.8 minus 7.43, and that comes out to be minus 29.23, minus 29.23 degrees. So this can also be expressed in rectangular form. 2.322 and angle minus 29.23. This is 2.026 and minus j 1.134 ohms. So we have determined uh, all the three combinations, three impedances in the equivalent Y combination. So let's now redraw this diagram without the lower delta combination and using the equivalent Y combination. So for example, we have uh, let me draw it here. So we have the upper delta remains the same, right? Or rather upper two branches remain the same, This is J4 ohm, this is minus J3 ohm, right? And we have transformed this delta combination here into this equivalent Y combination here. So we remove this delta combination and use the equivalent Y combination, right? By equivalent combination, we mean the voltages here and the potential difference between these uh, points A, B, and C will remain the same. So we have this Z1 here, and then we have a Z2 here and a Z3 here, right? And this is Z1, this is Z2, this is Z3, right? So let's call this figure 3. This was our figure 2. So we are to find this current I here. So as you can now see, this branch, this J4 ohm, is now in series with this impedance Z1. Similarly, this impedance minus J3 ohm, this branch is in series with this branch containing Z2. And these two branches and these two are in parallel with each other. So we can first find this series impedance here, equivalent impedance of this series combination, then the equivalent impedance of this series combination, then the equivalent impedance of this entire parallel combination, and thus add this to Z3 to find the equivalent impedance. So let me rewrite Z1, Z2, and Z3 here. So Z1, so as we are going to add these impedances, so I will use the rectangular form, right? So Z1 is equal to 2.187 plus J 0.106 ohm, and Z2 is given by 3.7 plus J 1.69 ohm. This is Z2, and Z3 is given by 2.026 minus J 1.134 ohm. So let's call this series impedance of this series combination to be Z4. So Z4 is equal to J4 plus Z1. So this is, let's call this uh, Z4, and this was 30 angle 0 degree volts here, right? So Z4 is equal to J4 plus 2.187 plus J 0.106 ohm. So Z4 is equal to 2.187 plus J 4.106 ohm. So in the polar form, this will be 2.187 and 4.106. This is 4.652, 4.652 at an angle of 61.96 degrees ohms. This is Z4. Similarly, let's call the impedance, equivalent impedance of this series combination to be Z5. So Z5 is equal to Z2 minus J3. So Z5 is equal to Z2 minus J3. So, 3.7 plus J 1.69 minus J3. So Z5 is equal to 3.7 minus J. So 3 minus 1.69. So that is 1.31 minus J 1.31 ohms. So Z5 is equal to in uh, in polar form 3.7 minus 1.31, and that is 3.925, and the angle is minus 19.5 degree ohms. So this is Z5. So we have now uh, found the equivalent impedance for this series combination, right? So next we can determine the impedance of this parallel combination of Z4 and Z5, right? So let's call the impedance of the parallel combination to be Z6, and that is equal to Z4 Z5 divided by Z4 plus Z5, and Z6 is equal to Z4 multiplied by Z5. So Z4 is 4.652 angle 61.96 degrees multiplied by Z5, which is 3.925 at an angle of minus 19.5 degrees divided by their sum. So we have the rectangular form also. So for the sum in the denominator, we use the rectangular forms. So that is 2.187 plus J 4.106 plus 3.7 and minus J 1.31. So Z6 is given is equal to 4.652 multiplied by 3.925, and that is equal to 18.2591, and the angle is 61.96 minus 19.5, and the angle is 42.46 degrees divided by, let's sum the first the real part, 2.187 and plus 3.7, that is 5.887, and then 4.106 minus 1.31, so that is plus 2 point plus J 2.796. So Z6 is equal to 18.2, let's round it off to 26 angle 42.46 degrees divided by, let's transform the denominator into the polar form, 5.887 and 2.796, and this is 6.517, and the angle is 25.4 25.4 degrees. So Z6 is 18.26 divided by 6.517, that is 2.802, and the angle is 42.46 minus 25.4, and that is 17.06 degrees ohms. So this is Z6, which is the impedance of this parallel combination. So we can redraw this figure now here. For example, if this is Z6, then this is in series with Z3. This is Z6, this is Z3, and this is our voltage source here, 30 angle 0 degrees volts, and this is the required current I here. So now the equivalent impedance Z equivalent is equal to Z6 plus Z3. So we need to calculate the rectangular form of this Z6 also. So that is 2.802 and angle is 17.06. So that is 2.68 plus j 0.822 ohms. So Z equivalent is equal to 2.68 plus j 0.822 plus Z3, and Z3 is 2.026 minus j 1.134. So Z equivalent is given by 2.68 plus 2.026, and that is equal to 4.706, and then 0.822 plus minus 1.134, and that is minus j 0.312 ohm. And in polar form, let's find the polar form, 4.706 and minus 0.312, that is 4.72, and the angle is minus 3.79 degrees ohms. So this is the equivalent impedance of this entire given circuit. So we can now find this current I from this voltage, 30 angle 0 degrees divided by 4.72 angle 3.7 minus 3.79 degrees. So that is 30 divided by 4.72, that is 6.36, and the angle is 3.79 degrees amperes. So the current I is 6.36 angle 3.79 degrees and 79 degree amperes. So this is the current I flowing through here in this circuit.